this video, I'm going to show you the application, how to make use of the semiconductor diode. Now, previously we have gone through semiconductor diode and the forward bias, so that you are able to allow current to pass through the diode. Where if you were to have a reverse bias, then the depletion layer will be taken and therefore no current could pass through it. Now, with me here, this is actually a tear down video over the AC DC converter. Now this is one of those small black color adapter to convert AC to DC that we use it for your perhaps printer, or in some cases in some speaker they will have a power source, or perhaps in your handphone charger you will see one of this. I've removed the cover to show you what is inside the black color rectangle cube. Okay, so here with me, this is actually the transformer, and then the side here, this is one of the diode. There are 4 of them, and the cylinder here is actually the capacitor, a big one. Okay, you may click on this window and then it will navigate you to another YouTube video. It will show you the better look at different various angle. Now, what is the application of diode? Okay, so diode or semiconductor diode, it works as rectifier. Okay. Now, how are they going to function as a rectifier? Okay, so it means, what does it mean actually? It means it allow only one direction of electron flow or current flow. Okay, rate change of electron is current flow from anode. Electron flow using a forward bias under forward bias arrangement. Right? So if it were to be a reverse bias, then it doesn't flow. Okay? Because of that, therefore, you'll be able to convert alternate current. Here in Malaysia, you will use 240 alternate current. This is a symbol for alternate current. You convert alternate current to direct current. Okay, direct current using this converter. So the function of transformer is, of course, step down 240 to 13. To get AC to DC, this is where you need diode. Right? Now, there are actually 2 different models you can use. One of it would be, or perhaps let's talk about how does it work. If your source here is alternate current, after you have stepped it down from 240 to 13 watt, it is still alternate current. So the graph would be still a sinusoidal graph, etc. Okay? What happened during the first cycle, if you carefully focus at the positive side, this is positive and negative. During the first half cycle, this is for one wave. First half cycle, it is positive. The next half cycle is negative. This is positive. Okay? So during the first cycle, positive, it will pass through. If you have only one, you will pass through it. And when it were to be the negative current, what happened? It will block it. So therefore, if you have only one, you have that flat, and then etc. the first half you see it, then flat out, and then the second one, etc. Okay, so if you are using one of it, therefore this is what will happen. So say for example, if you have a circuit, this is say alternate current. Use one diode, and then this is your your load, maybe a resistor, and then what happened? You want to see this profile. All you need to do is connect it to cathode ray oscilloscope, and then you were able to see the wavefront. You were actually seeing this. Okay, you will see supposed to have one, but then etc. Okay, it is missing because what happened? The first half cycle, positive, yes, this diode allows it to pass through. When it goes to a negative, when it were to be negative, then it blocks it. So therefore, no current detected over the load when you have one diode. And this is what it meant, or this is labeled, or this is being called half wave, because it's only half the wave comes out. Half wave rectification, because only half comes out. This half comes out, and you doesn't want it because there's a waste, isn't it? It's being wasted. So what happened? The engineers or scientists work around, and if they found that if you have two pairs in series and two pairs in parallel, like this, the first pair would be in series, and then this pair, they put them into parallel. Okay, and this were to be your output. To your CRO, and the input, let's use the input to be in the middle, it has to be from the middle. This is the input. It doesn't connect, okay. So in the middle, you will get a full wave rectification. Okay. Another way to illustrate this, two series, two pair, a pair in a series put in a parallel form, would be from what you have seen from your book. They arrange it in a diamond form. The diamond is hard to draw because all you need to do is you pull this end up and down, so it turns out to be okay. Alright, so you pull it up, then it will turns out to be like this, and then you pull it up, then it faces in this direction, and then okay, out, and then right, okay, and then here up, this one here, put it down, so it turns out to be this manner. It's a matter of rearrangement. Okay, then the middle, so this point to this point, this is to the point, and then this point to this point. If it were to be sinusoidal input, okay, then this end maybe just another color, or perhaps I use this color. This end represents this point. Let's connect to it, and then this end to this end to CRO, cathode ray oscilloscope, or you may want to put a load here. Okay, so this arrangement or this arrangement, they're actually identical. This is what is being called a full wave rectification. Full wave rectification. This is the arrangement where we use in this circuit. You actually 1, 2, 3, 4. 1, 2, 3, 4. You may want to click on this video and then look for the how does it look like. Okay, so why is it called full wave? Because if you have 4 of them, you will be actually getting the wave in this form. This is called a full wave because they invert the negative up already. Okay, alright, so this is how, and the difference between them would be if you use only one, then there's a half wave. You have all 4 arranged in this manner, 2 parallel, 2 series, then you get full wave rectification. You need to actually know how to arrange them. Normally it comes up in the objective question, so that you need to pick which one is the right arrangement, or in subjective question, paper 2, you need to draw how it should be arranged. Either you draw it in this form or this form. I think this is the easiest to recognize it, easiest to draw, because series and then parallel them. Okay, so something that is not yet complete, because in order for you to say it's a direct current, what happened was the current goes up and then it climbs down. What happened if it were to be current over time, or you connect it to a light bulb? What happened? You get maximum, increased maximum, and the minimum brightness. Then you get flickering. This is not what you want, right? So in order to overcome that problem, there's a process in SPM, physics, SPM, we call it a smoothing process. Smoothing of rectification. Okay, now let's go back to the wave earlier. We have full wave rectification. It's a sinusoidal graph. Okay, I know. Says I say this is a current, right? So if you connect to a light bulb, then it is not good, because you have maximum, minimum, maximum, minimum. You get maximum brightness and then drop to 0 and then maximum and then minimum. This is not good. You don't like that. You want continuous current. Okay, so one way to do that would be they introduce the use of capacitor. Okay, what a capacitor does is store electron, or they store charges, or electron, okay, or electron. So how are you going to introduce a capacitor? I mean, if you look carefully, this is what it means by that. This is a capacitor, a cylinder, a big one indeed, to smooth it. Okay, so how does it do? So I'm not going to use a full wave rectification for simplicity. I'm going to use only the half wave rectification in terms of circuit. So say for example, I have only Okay, this much. Okay. They introduce a capacitor parallel to the circuit before you have your load or light bulb, so that parallel form connect with CRO. Now, what you will see here would be during the first half cycle, the electron or the current used to power up the load, this is your load. At the same time, it charges up your capacitor during the first half cycle. Okay, so what happened? Well, this is the driving curve. Perhaps it's not the actual curve yet. Okay, so what happened? Oh, it doesn't look like that. Okay, it should look like this. We sketch a driving curve. Okay, the sinusoidal. Okay, now current. First half cycle, what happened? It charges up. It charges up. Charge up not only the capacitor but also your load, right? And then when you have the negative half cycle comes in, it block it. It doesn't come, right? Ordinarily, ordinary condition. Well, during this period of time, what happened? No current passed through it, but the electron is being stored inside the capacitor. Those electrons would be released or discharged from the capacitor. This is discharged from the capacitor, and therefore giving you the moment before it really drops, it actually discharges to a certain level. It depends on your capacitance. Then once your positive comes up, then it will power up again. At the same time, it charge up your capacitor, and then discharge, charge, and discharge. So here you will be able to see a smooth line if your capacitance of your capacitor is high. That's why you need a big capacitor that I actually shown over here, in the video. Okay, so for this case, you have full wave rectification. What happened? That would be like this. Initially, when there's no charge, and then you need to charge it up. Then what happened? It will actually discharge, discharge, and discharge. So you will actually see quite a smooth graph. Okay, so you will never actually fall. You will never go down to a certain value. You will always maintain at a constant current. Okay, so this is how it works during the positive half. I'll jot down some notes for you. Okay, during the positive half cycle, the capacitor is charged. because they are in parallel. The parallel capacitor is being charged up. During the negative half cycle, the capacitor is being discharged. Okay, therefore giving you a smooth current, or in a DC form. Okay, so how do you determine how smooth is it? It is determined by the capacitance. Measure unit in farad, microfarad, picofarad, it depends. F-A-R-A-D, that's actually the capability of the capacitor to store electron or charge. Okay, I think that's all from me this time round. You may want to go through the chapter by chapter exercise, 8 to 10 questions for this video. The topic discussed in this video, rectifier, full-wave rectification, as well as smoothing. If you were to be the first time watching my video, kindly subscribe to my channel. It's free, and I appreciate the thumbs up. Stay tuned to my next video.